pipelining technology is. So the pipelining technology was introduced in the Intel processor of 8086. Okay. So we will go back just a slide back from our previous discussion last Thursday. Okay. All right, so you can see the difference between pipeline and without pipeline. So it's called non-pipeline. So whenever, because the operation of the microprocessor involved fetching and execution, fetch and execute, fetch and execute. So without pipelining, the fetch and execute is done until the complete process of fetch and execute done, and then only the next fetch and execute is continued. But using the pipelining technology, so the fetch and execute started first, and then before the execution is already finished for that one, another fetching can be done. Okay, so that's the meaning of the pipeline technology. Okay, so Intel have done that by splitting the internal structure of the 8086 microprocessor by two units, okay, two sections, which one for EU, which is the execution unit, and the other one is using the bus interface unit. Okay, and those two sections work simultaneously, all right, where the BIU is for accessing the memory and peripherals, okay, so memory and the devices, while the EU executes instructions previously fetched. Okay, so meaning that, so you saw that we have fetching and execution. All right, so the EU, so EU is doing the execution part, and then the BIU is actually on the fetching. Okay, so BIU working on the fetching part. All right, so this means, so BIU must always be ahead of the EU. Okay, so the BIU has a buffer. So a buffer is like you need to queue a little bit ahead of the EU. All right, so the buffer size is 4 bytes long in 8088 and 6 bytes in 8086. Okay, so in the 86 processor, we only have the part two stages, okay, which I just shown. It is fetch and execute. But in more recent computers, the more powerful computers, it can have many stages. Okay, if the instruction takes too long to execute, the queue is filled to capacity and the buses will sit idle. Okay, so when the execution takes too long, so actually you cannot start the next process without fetching the next information. So what the microprocessor will do, so to avoid the wasting of time, so it must flush the queue. All right, so it must flush the queue, and then we can have a jump instruction. So the jump instruction meaning that without having finished the execution, okay, another instructions already be executed. Okay, so here where the BIU starts to fetch the new information, all right, from the new location in the memory. Okay, and the information fetched previously is discarded. All right, so the EU is always waiting for the BIU to fetch for the new instruction before EU can do the execution. Okay, so this is called as a branch penalty when we have the jumping of the instruction. Okay, but however, if there are too much jumping, then the efficiency of the program is reduced. Okay, so that's about the pipeline technology. And then we look at the register. Okay, so as we learned before, the register is used to store the fetch information from the memory, okay, for temporarily before it is processed and executed by the microprocessor. Okay, so 1 or 2 bytes of so the register is used to store the information temporarily, and then either it can be 1 or 2 bytes of data can be processed. So we need to have the address of the data. Okay, so the address of the data is from the, we obtain that from the address bus. Okay. Okay, so for the general purpose register in 88 or 86 processors can be accessed as either 16-bit or 8-bit registers. Okay, this is for general purpose register, but not for other registers. So you need to distinguish between general purpose register and also other types of register. For other types of register, it can only be accessed as a full 16-bit. Okay, so that's the difference. So for the general purpose register, it can be either 8 or 16-bit. But for other registers, it must be 16-bit. Okay, so the data type can be either 8 or 16 bits. Okay, but for example, if we have 12-bit of data, so what will happen? We will use the 16-bit, but for the highest 4 bits, okay, will not be used. So for that, it will be set to 0. Okay, so this is an example of 8-bit and 16-bit register. As you can see there, so this is 8-bit, okay, part of that. Either we use this part, okay, or we use both. So that's how it can become either 8 or 16-bit. Okay, so for the 16-bit register, so there is a notation of the letter, okay, for each register. So for here, let's say we have the AX, okay, AX and A hash and AL. Okay, so for AX, so it's used for accumulator. All right, and you can see here, the accumulator for here is 16-bit. Okay, so it's a 16-bit accumulator. All right, it accumulates the information or accumulates the data. And then for A hash, all right, so A hash usually, okay, I relate to here. Okay, so for AX is all of that, okay, all of this. So let's say this is for AX, and A hash is only contains on the higher bit of the 16-bit register. So it is 8-bit, but it will take only on the higher 16-bit of the register. So take for 8-bit, and for the lower, the AL, so L is for the lower bit indicator, H for higher bit indicator. So we take only up to D7. All right, so we take the 8-bit at the lower bit of the register. Okay, so the letter, okay, the letter here, okay, A, okay, now A is for accumulator, and B is for base addressing register. Okay, and then C is for counter in loop operation, so it will increase 1, 2, 3, 4, and so on. Okay, so B is for base addressing. So as we learned, so we need to address, okay, each information. So that's the B. Okay, and D is points to the data data in the input and output operation. So D is for the data. Okay, so you can distinguish between A, B, C, and D in the register. So remember that. So A for accumulator, B is for base addressing, C is for counter, D is for data. Alright, so as I said, so for the general one, so we can have either 8 or 16 bit, but for the others, it must always be 16. Okay, so for 16, of course, we have X, 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 X over here. So for the 8 bit, we must have 2 complements. So always have H and L, H and L, H and L, and H and L. So for the general purpose register, we have the function of A, B, C, and D. All right. And then for the pointer, okay, for the pointer register, so we have the S and B. So S for stack pointer and B is for base pointer. We will go through on the definition of other register, okay, later. Right. So for now, I just introduced about what are the types of register that are available on the 86 processor. Okay. We also have the index register, which is S and DI. Okay, SI and DI. Okay. I is for index. Okay, index. All right, and then S is the source index and D is the destination index. Okay, we also have the segment register. So we have C, D, S, and E. Okay, we have code segment, data segment, stack segment, and extra segment. Okay, and for instruction, we have the IP. So we have the instruction pointer. So that's for instruction register. And we also have flag, the register. So we have the register names as FR, flag register. Okay. All right. Since we are now going to program on how to use, okay, how to fetch and execute the information from the microprocessor. So there must be a programmer to program that, okay, what to do and what to do, because the computer cannot work alone, because it's not like human, okay, because you have your own brain and then you can think what you need to, what you can do, and then what you need to do, what you plan to do. Okay, so the computer must wait for the instruction. Okay, so the computer must wait for the instruction. All right, so it is like a car. All right, so in order to move the car, you must start the engine. All right, even though it is an, let's say it is an autonomous car, you must even start the engine first. All right, before it can move. All right, so that's actually the computer, the microprocessor. Okay, so you must have a human as a programmer to program the microprocessor to work, okay, to work based on the instruction given. Okay, so as you learn, the CPU can only work in binary, okay, which is 0 and 1. Okay, it is okay, so the computer can work in very high speed using the binary number 0 and 1. It is tedious and slow for human, however, to deal with 0 and 1. Okay, because if you code in 0 and 1, it will take you a very long time. Okay, even if you want to, let's say, stating number 4. Okay, so you must code, it is 0, 0, okay, 0, 1, 0, 0. Okay, so that's number 4. So instead of typing number 4, you must type 0, 1, 0, 0. So if, let's say, it's 4 million, of course, it will take you time to write the code. Okay, so that's why it is very slow for human to program the computer in the binary. Okay, so this binary, the program of binary 0 and 1 is called the machine language. Okay, so the early programmer actually did the program. He did the program in the machine language, which is in the 0 and 1, the binary number. Okay, and then after that, the assembly languages were developed. Okay, so this provides the mnemonics for the machine code. Okay, so the mnemonic is typically used in computer science and engineering literature to refer to codes and abbreviation that are relatively easy to remember. Okay, so the assembly language is referred as a low-level language because it deals directly with the internal structure of the CPU. So we use the assembly language to program the CPU. Okay, but to convert what we program to the binary code, okay, we need to have a program called as an assembler. All right. So to program in the assembly language, the programmers must know the number of registers and their size. Okay. So the programmer need to know how many registers are inside those microprocessor. Okay, and the size. Okay, is it 16-bit or 8-bit? Okay, as well as other details inside the CPU, such as the memory, all right, and the devices that is connected. Okay, so today there are many different programming languages, such as C or C++, Basic, C#, and etc. Okay, so all of those are the high-level languages because the programmer does not have to be concerned with the internal CPU details. Okay, so the assembly language is a low level because it is used for giving the instruction to the CPU. Okay, other codes is only on the software level, right? So only for the software level. So that's the difference between high level language and also the low level language. Okay, so for high level language, still it must be translated into the binary, okay, into the machine code, but the program is called a compiler. Okay, so for low level it's called as the assembler, but for the high level language it's called as the compiler. So to write a program in C, one must use a C compiler to translate the program into the machine language. Okay. There are numerous assemblers available for the translating x86 assembly language programs into the machine code. Okay, one of the most commonly used assemblers is MASM by the Microsoft. Okay, all right. So the chapter on that, all right, is designed to correspond to the Appendix A in the debug programming. So you can look at the book. So refer to the Appendix A debug programming. So you can look at the codes of the assembly language over there. Okay. All right. Now we're going to go deeper with the assembly language, okay, because actually most of the course content are dealing with the assembly language. All right, where do the quiz on the assembly programming later, okay, which will be part of your grades. Okay, so the assembly language consists of a series of lines of assembly language instruction. Okay, so the assembly language instruction consists of a mnemonic, optionally followed by one or two operands. Okay, so the operands are the data items that is manipulated. Okay, so the mnemonics are commands to the CPU telling it what to do with those items. Okay, so it is an instruction, okay, which is using the mnemonic. and also operand. Okay, mnemonic and operand. Okay, operand are the data that is manipulated. Okay, so the two widely used instructions are move and add. So this is what we involve in the fetch and execute. All right. So like before, so we have move and add, move and add, move and add, fetch and execute, fetch and execute. All right. So that's the most commonly used instruction. Okay. So let's look at the move instruction. So the move MOV instruction copies data from one location to another, right? So for example, we have this format, MOV destination, okay, comma source, and double comma copy source operand to destination. Okay, so this instruction tells the CPU to move, right, in reality copy, okay, the source operand to the destination operand. Okay. For example, we have the instruction. Okay. So as you learn, MOV space DX, comma, CX. Okay. So what is this? All right. So as we learn, what is D? D is data. So X is 16-bit, right? So data in the 16-bit. So we need to move the data in 16-bit, and C, X. C is for counter for 16-bit. Okay. So it means here, this instruction means copies the content of register C, okay, to register D. Okay, register C to the register D. Okay, so mean that move from C to D, from C to D. Okay, so what will happen? Okay, initially, let's say the CX content, you have 0, 1, 0, 0, okay, but at the present time, let's say the X is 0, 0, 0, 0, and then 1, we have the move instruction. Now the DX become 0, 1, 0, 0, in which the DX will be similar value as the CX. Okay, all right, so we look further. So we expand the example. So let's say this program CL, okay, the CL, which is the low bit, or which is the 8-bit, okay, lower 8-bit of the 16-bit register. So we load that with the value of 55H. So H stands for hex. Okay, remember that. So we program the assembly language in the hex bit because it is 16-bit. Okay, so the maximum can be is of course for the 16-bit it is F, okay, F and F. All right. So we have FF, FF. Okay. So for example over here. All right. So we have 55. Okay. Move into register CL. Okay. And then that value. Okay. And then CL. You move DL, comma CL. So mean that now DL becomes 55H. Okay. And then move AH, comma DL. So now the content of AH becomes 55H. Okay, and then now we move from AH to AL. So move AL, comma AH. So now AL becomes also 55H. And then move BH, comma CL. So we have now the content of, okay, you can look over there. What is it? So the content of BH now also 55H. and then we also have CH. Okay, we also have move CH, comma BH. So the content of CH now becomes also 55H. All right. So this is, so previously it was on the 16-bit registers. Okay, now we look for the, this is for the 8-bit register. Okay, now we look here for the 16-bit register, because 16 bits the register, so the second letter mention that the number of bit for the register, which is 16. So 16 bit is X. So let's say we have, okay, now we have FFFF, all right? So we have the, okay, so we have the 16-bit register. And now example, we want to move the value of 468F. Okay, 468F, they move that into CX. Okay, all right, we look here, okay, as CX is divided with the CH and CL, so mean that the higher two bits, okay, CH is now equals to 46 and CL equal to 8F. Okay, now, all right, you look there, so move AX, comma CX, so now the content of AX will be similar to CX, okay, which is 468F. All right, DX also will be similar, and then move BX. Okay, now BX will be the same as AX as DX as well. Okay, and then now we have the DI. Okay, DI to BX. All right, so as you remember, it is not a problem to move between register as long as the register is on the similar bit. Okay, so now this is an instruction register, okay, DI, okay, and SI, okay, and then we can also move to DS and BP, the pointer, right? So you can look over there. So actually you can move, okay, we can move between the same bit register, okay, so it's not a problem as long as the number of bit within registers are similar. Okay, so right, as I said, this is what I said. All right, so the data can be moved among all registers as long as the source and destination registers match in size. Okay, except the flat register. Okay, so for example, there is no such instruction as move FR, AX. So the general register cannot be moved to the flat register. All right. Okay, so let's have a look. Okay. We also cannot move the content of 16-bit register into an 8-bit register. Okay. For example, over here, you want to move the content of DX. Okay. So DX, of course, it is a 16-bit register. You want to move that to the AL, so which is a 8-bit register, so it cannot be done because it violates the rule. Okay, but we can move the content from 8-bit register to the 16-bit register. Okay, so that is fine. Okay, using the move instruction, data can be moved directly into non-segment registers only. Okay. Okay, we look over here. So we have couple of legal and illegal instructions. Okay. For example, move AX. So of course, AX is 16-bit register. So we can move that number 58FC. Okay, DX, we also have no problem. because that's also the 16-bit register. Okay, 924B, we don't have any problem with that. Okay. All right, so we also have the, okay, we also have the BP, right? Okay, BP 2459, all right, so that's okay. All right, we look over here. This one is illegal, all right? Because what? Because we cannot move the data directly into the segment register. So DS, CS is the segment register. Okay, so we cannot do that. So that's why it is illegal. It cannot be directly moved to that. It must be following some other instruction first before it can be moved to that DS and CS. Okay. All right. So that's another rule. Okay. Also, the values cannot be loaded directly into any segment registers. Okay. Okay. So we have so this is special case for the segment register. So we have CS, DS, ES, or SS. Okay. So how we can do that? All right. So how we can do that? So to load a value into the segment register, load it to the non-segment register, then move it to the segment register. Okay. It still can be done, except that it must be loaded to other register first. Okay. Other register first, that is non-segment register. For example, we have move AX, do 2345. Okay, so we move now the value of 2345 into AX and then move DS, AX. Okay, it can be done. All right, so that's the example. All right, so you need to remember that. So there are certain rules on the assembly programming for the move instruction. Is full for if a value less than FFH is into 16-bit register. Okay, the rest of bits are assumed to be 0. Okay, all right. So if a value less than FF move into 16-bit, the rest of the bit are 0. So meaning that, okay, this is only for the value that is for 8-bit. Okay, because it is an 8-bit value, right? For example, we have move BX, 5. So 5 is considered the least significant bit. Okay, the result will be, okay, so because BX is the general purpose register, so we have BH and BL. So the content of 5 will be inserted to the lower bit, BL. Okay, BL will be equals to 0, 5, and then BH will be equals to 0, 0. Okay. All right. Also, if we move a value that is too large into a register, this will also cause an error. Okay. For example, we move the value of more than 8-bit into BL, for example. So BL can only accept 8-bit. So let's say we have 7F2. Okay, that is inserted into the BL. So that is illegal. Okay, so how to make it legal? Okay, so how to make it legal? Okay, what is the maximum? Okay, I have a question for you. What is the maximum data? Okay, what is the maximum value that can be inserted to BL. Okay, tell me, what is it? Any of you? Any of you wants to answer that?
16.
16. No, I mean in terms of value. So let's say we have, okay, give me the value. Let's say 16H, all right, or 26H. So what's that value? Because it is should be an 8-bit. So what's the value? Anyone?
In hex, doctor.
Pardon?
You're asking for the value.
Yes, value that can be moved, the maximum value that can be moved to BL.
BL.
So to make this legal, all right? So you have move BL, comma 7F2, that is illegal. So how to make it legal? I said for the maximum that can be moved to BL.
Is it 0xFF?
0xFF. Why you have the X there?
Oh, wait, sorry.
Okay.
Just FF.
Yes, that's
Is
good.
it?
Yeah, that's correct. Okay. So actually, what you should do, so for the maximum value, so you have move, okay, BL, comma, F, F, H. So this is the maximum data that can be legal. Okay. All right. So we look at the second example. So we have moved AX2FE456H. Of course, that is illegal. So how to make it legal? So to make it legal, you must ensure that it is only 16-bit. All right, it is only 16-bit. So how to make it 16-bit? So either we remove two numbers from there. Okay. So this will be legal. Okay. All right. So that's one way on how to make the statement legal. So do you get it? Okay.
Yes, doctor.
All right, good. Okay, so now we move to the add instruction. All right.
Doctor,
Yes. Do you have any question?
how can we know that FFH is legal?
Because F is the maximum value for the hex, right? You remember the hex? So hex is from 0 to F. Okay?
Okay.
Okay? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then A, B, C, E, F. Okay? So F is the maximum value for the hex. Okay? Because H here is denoted for hex. All right. So we 8-bit. So here is consider one of these is considered a 4-bit. And then this is another 4-bit. Okay, so we have 8-bit. All right. So for 16-bit, we have 4. 1, 2, 3, 4. Okay. So what's the maximum for this? So the maximum for that is
4 F
yes, move AX, comma F F
F F
F
F.
F and H. Okay, so this is the maximum for X register. So X is 16-bit. Okay, remember either if L or H, it can accept only 8-bit. Okay, it can accept only 8-bit. All right. So that's it for the move instruction. Okay, let's say now we have the add instruction. Okay, so add destination, comma source. So it's like the move as well. So we have what we want to add. So we add from here. Okay, move to here. All right. Add tells the CPU to add the source and destination operands and put the result in the destination. Okay, to add two numbers such as 25H and 34H. Each can be moved to a register, okay, then added together. All right. So now we want to move 25 into AL. Okay, so we put that 25, okay, into AL. Move 34 into BL. Okay, and then add AL and BL. Add BL to AL. Okay. Previously, AL, okay, AL is 25, and now BL is added to this value. So 25 is added to 34. All right, so we have 59. Okay, now the results is AL becomes, okay, 59. Okay, and then the BL still remains at the 34H. Okay, so remember that the source, okay, the source value will not change. All right. Okay, so the program, okay, can also be written in many ways. So it depends on the registers used. For example, okay, we have move. So we move the 25, value of 25 into the DH. All right. And then now we move the 34 to CL. All right. And then the content of CL is added to the DH. So DH now becomes 59. All right. And CL becomes 34. Okay. All right. Is it necessary to move both data items into registers before adding them together? No, it is not necessarily. Okay. So we don't necessarily to move the data items together into register, okay, without doing the addition function. We can just straight add to that. Okay, for example, we only have one. Okay, now DH, right? Now DH. So DH now is not been put to any value. Now we move 25 into DH. Okay, now DH becomes 25. And then we want to add another value to that DH. So we add DH, comma, we put 34. So now the DH 59. Okay. So what happened here? So DH becomes 59. But when we don't add the value of 34 to any other register before, so we don't know what is the values added to that DH. We only know the result. So the result is that 59. Okay. So that's the difference between adding directly to the register and then adding by moving first into other register and then add that to another register. So that's another way to add the data. Okay. All right. So the case above over here, so this case is called as the intermediate operand. Okay. So this is called as the intermediate operand. Okay, so the 8-bit registers can hold numbers up to FFH. Okay, so this is the maximum value, that's as I said. All right. So for numbers larger than FFH, right, 255 in terms of decimal. Okay, so we have a, all right, so we have a 16-bit register such as, okay, AX, BX, CX, or DX. Okay, so we must use the 16-bit register. So why is this 255 decimal? Okay, why is this the 255 decimal? So this is how many bit? It is 8-bit. All right. So what is the total number for the 8-bit? All right. The maximum number will be 2 to the 8, which is 2, 5, 6. Okay. So because the number is from 0 to 255. Okay. So that's why, okay, it will be in terms of 255 decimal. All right. Okay, let's look here. So we have another number. Okay, so now we have this number must be put into the 16-bit register. So we cannot use the 8-bit register. Okay. So first we move, okay, this value 34E into AX, all right, and then move 6A5 into DX. And then we want to add the content of AX into DX. So we just add that. Now, what we have, okay, so we need to add the hex number. So E with 5. Okay, so E is already how many? Okay, E is already 14 plus, okay, 5. So it's 19. So 19, so we minus 16. All right, minus 16 because it is a, it's a 16 bit number. Okay, 16 bit. All right, so we need to minus 16. So that's why we have 3 over here. And we add 1. So we have 3. So we have 3, we add 1 to here. All right, so now we have A plus 4. Okay, how much is A? So 9, 10. Okay, 4, so it will be 15. So 15 is F. Okay, and then lastly 6 plus 3 will be 9. So that's how you get the dx. All right. Okay, so the ax will still remain as 34e. Okay, is it clear? So you are guys okay up to now? So this is the most important subject that you need to understand before we can proceed further. All right, the move and add instruction. Okay, because you're going to design a program. Okay, so that work. A program that work. Let's say you are having a situation later, right? You want to make a decision. Okay, so this is just the basics on what you need to do. This is just the computation, moving and add instruction. Okay, so if you are not clear at any point, please ask me. Okay, so for any 16-bit non-segment register to have been used to perform the action here, let's say, okay, 34E, so we move that to CX, okay, and then we add those values 6A5 to CX. So we add 34E with 6A5. Okay. All right. So that's why this called as the accumulator, because it can accumulate the value. All right. So it can accumulate the value. So you can just add. Okay. So you can just add to that value. So you will get another 16-bit value.
Doctor,
Yes.
what is the difference between segment register and non-segment register?
Okay, so we only have one type of segment register. So as I mentioned here, okay, so we have here, all right. So we only have segment register is using the name of CS, SS, and ES. So this is only the segment register. Other than that, this one and these ones are non-segment register. Non-segment. Okay, these are the non-segment register. So hope you're clear. That one and also that one. Okay, for general, so it's non-segment register. Pointer is also non-segment register. Index is also non-segment register. Instruction is also non-segment register. Flag also non-segment register. But you need to notify that we normally cannot use flag, okay, for adding the number. But we can use all of the other. Let's say the general one, pointer or index or instruction, we can use that for addition. Okay. So let's say here, as I just mentioned, so we have okay. All right, here the data can be moved along all registers as long as the source and destination registers match in size, except in the flag register. Okay, so this is illegal. All right, other than that, it can be used. Okay, for example here, so we can use other than that, except for the segment register, which is illegal. Okay, so it is illegal to perform the move and add instruction to the segment register. Okay, so for example, so you have general register AX and DX. SI is the instruction, so this is the pointer register. Okay, CX and BH is also the general register. Okay. Okay, so the register of AX sometimes is called as the accumulator. All right. So usually we use the AX to perform the accumulation function. Okay. So now we need to look at the program segments. Okay. A typical assembly language program consists of at least 3 segments. Okay. A code segment which contains the assembly language instruction that perform the task that the program was designed to accomplish. Okay. So it contains the code segment which perform the task that the program was designed. Okay, and the data segment which is used to store the information to be processed by the instructions in this code segment, and a stat segment, okay, which is used by the CPU to store information temporarily. Okay, so remember that we have the 3 segments: code segment, data segment, and stat segment. Okay, the code, data, and stat segment. Okay, stat is to store the information temporarily, data to store the information, okay, code is to perform the task. Okay, so that's 3 functions of those 3 segments. Okay, a segment is an area of memory that includes up to 64 kilobytes and begins on an address evenly divisible by 16. Okay, so such as address ends in 0H. Okay, and 85 processor address a maximum of 64K of physical memory since it had only 16 pins for address lines. Okay, so this is like the address bus. All right, so we have 16 pins. So we have 16 pins. So it's like the highway. All right, so this is a highway. So this one will be accessed to the memory. Okay, so the maximum we can only have up to 64K of the memory. Okay, because each of these are binary. Okay, so there is 0 or 1. So 2 to the power of 16 is equivalent to the 64. Okay, so the limitation was carried into the 86 processor designed for compatibility. Okay, in 8085, okay, there was 60K bytes of memory for all code, data, and stat information. Okay, in 86, there can be up to 60K bytes in each category. Okay, so meaning that we have 64 times 3. Okay, we have 64 times 3 of byte of information in each category. But in 85, only 64 bytes, 64 kilobytes is shared for all code, data, and stat segment. Okay, there are 3 types of address mentioned frequently in 8086, right? So the physical address, right? The 20-bit address actually on the address pins of the 86 processor decoded by the memory interfacing circuitry. Okay, so because it is a 16-bit capability, so the address can have a range of 0, 0. Okay, so we have 20-bit, 20-bit address. So we add one more. Okay, because 20-bit address can be address pins for the 86 processor. So it can have one more here. So you look if we have 5 number. So we have 5. Previously, if 16 bit, we can only have 4. So here it's only 000H to F, 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 F. Okay, so that's the maximum for 16 bit. But for 20 bit, then goes up to 5. Alright. Then the actual physical location in RAM or ROM within the 1 megabyte of the memory range. Okay, so it can support up to 1 megabyte of memory range. Okay, so we also have another one. So we have physical address and we also have a offset address. Okay, for the offset address, okay, a location in the 64 kilobyte segment range. Okay, so this one is a 64 kilobyte segment. So it range from 000 to FFF. So it's only for 16 bit. Okay, so it's only 16 bit. So this is 16 bit. All right, we also have the logical address, okay, which consists of a segment value and an offset address. Okay, so we have 3 types of address in 8086: the physical address, offset address, and logical address. So these addresses are related to the way we access the memory. Okay, as you remember that we have the address bus. Okay, this is how we are using the address to, okay, using the address to fetch the information. Okay, all right. So to execute a program, okay, the 86 processor fetches the instructions, the codes and the opcodes and the operands from the code segment. Okay, so we take the processor will first take the instruction from the code segment. Okay, so the logical address of an instruction always consists of a CS. Okay, the code segment. Okay, this is what we use for the register for the segment, right? The segment register. We have the code segment and IP, instruction pointer. Okay, so usually it's shown in the CS double dot IP. All right, the physical address for the location of the instruction is generated by shifting the CS, okay, shift the code segment left 1 hex digit, okay, and then adding it to the IP. Okay, so the IP will contain the offset address. Okay, the resulting 20-bit address is called the physical address since it is put on the external physical address bus pins. Okay, so this is how the fetching is done in the 86 processor. Okay, let's look at this example. Okay, so let's say we have these two number, okay, in the code segment and also the instruction pointer. So in the code segment CS we have 2500, okay, and the IP we have 95F3. Okay, so the offset address contains in IP is 95F3. Okay, the logical address, okay, logical address is CS, okay, double dot IP or 2500 double dot 95 F3, okay, and then the physical address will be, okay, because the physical address will be 20 bit, okay, so we add this, so we add another 0 which is already offset by the CS. So what's that meant by this statement? Okay, so the logical address is presented in this format. Okay, the physical address, okay, is generated by shifting the CS left one hex digit, okay, one hex digit, then adding IP. Okay, so the IP contains the offset address. Okay, so this is the IP contains the offset address. So this is the offset address. Offset. And then this is the logical address. Okay. And then the physical address will be, you add 0 to here. Okay. You add another 0, it become 2500, and add 0, and then add with that number. So this is what is the resulting physical address. Okay. Let's say we want to calculate the physical address. So we have the CS. Okay. So this is how we do it. So start with the CS. We have 25000, sorry, 2500, and then we need first to shift the CF one hex digit. So we shift to one hex digit, so it becomes 2500, and then we add another 0 at the back. Okay, and then we add the IP instruction pointer, this number, and then this is the resulting physical address. Okay, so the microprocessor will retrieve the instruction from the memory location starting at 2E5F3. Okay, so that's how the fetching working principle working on the 86 processor. Okay, so since an IP, okay, so this is the IP, can have a minimum value of 000H and a maximum of FFFF, the logical address range in this example will be, okay, from 2500, okay, to 00, from 20 to 2500 to FFFF. So that's the range of the logical address. So you need to be able now to distinguish between the logical address, okay, the offset address, okay, and then the physical address. So what is the offset address over here? Okay, what is the offset address? So can you obtain the offset address from the logical address? Any one of you?
IP.
Yes, IP. IP is the offset address. So basically from here, this is the logical address. So this is the offset address. So offset address. Okay. So you can obtain also your physical address. So what is the physical address of this? So the physical address of this is 2500 and 0. Okay, so that's your offset address. How about this one? Okay, so your offset address will be 25000 added with FFFF. F, F. So it becomes F, 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 and this one is, what is it? So 20. So 20 minus F, so it will be 4, and then it will be 3. Okay, so that is your physical address. Okay, so this is what I just mentioned. All right, the highest memory location will be 34FFF. Okay, and the minimum one will be 25000. Okay, so what happens if the desired instructions are located beyond these two limits? Okay, how about if the instructions beyond that two limit? So the values of CS must be changed to access those instructions. Okay, so we look at the example. Okay, if CS is 24F6, okay, and IP is 634A, okay, we need to show the logical address. So the logical address is simple. So we just take this, then double dot with this, okay, and B is the offset address. Offset is this one. Okay, so this is the offset address, calculate the physical address. So you just sum up this one and that one, so you get the physical address. Okay, so this one is your physical address, the lower range and the upper range of the code segment. Okay, so for the lower range, okay, what is it? So the lower range of the code segment is, okay, you have 24F6, okay, add you add that with 0000. So you add 0 at the back of there, and then the maximum one will be 24F60 added with FFFF. Okay, so you obtain this value. Okay, so
Doctor,
yes,
how come it gets 0 when the CS is only 2 for F6?
what's your question again?
Why it added 2 for F60 and then
Okay, so this is actually we look at the range, okay, range of the code segment. So because this one actually we need to look at the physical address of that. If you ask about the upper range, okay, so right, the upper range. So this one we need to add FF. So we actually adding the physical address to that. Okay. So this is actually we look, so for the code segment over here, this is just the information stored in the register. Okay. But the real physical address of that, to look at the physical address on the lower range and also upper range. Okay, that's actually the value of the physical address, because this value of physical address is put on the address bus. Okay,
so the before we edit we must shift the CS first, Doctor.
yes, because this is the CS which is stored in the register. Okay, when we were asked about the lower range of the code segment, so we need to shift because we need to find the physical address. Okay, so 24 F6, so we shift, so we have 24 F60, and then we add with 0 0 0, that's for the lower range, or for the upper range we add with F F F F. So we add this F F F F. Okay, so that's actually the low limit and the upper limit of the code segment. So as just mentioned here, okay. So this means the lowest memory location of the code segment, okay, of the code segment above will be, okay, 25000, and then the highest memory location will be 34FFF. Okay, this is actually asking about the memory location of the code segment. Okay, all right. So the code segment here is the one that contains inside the memory. Okay. Okay, in the next code segment, okay, CS and IP hold the logical address of the instructions to be executed. Okay, then the following assembly language instructions have been assembled, okay, translated into the machine code and stored in the memory. Once we do the coding with assembly language, okay, then the assembler do the job to translate the code into the machine code and then stored in the memory. And then the 3 columns shows the logical address. Okay, so this is the logical address that is shown. All right, CS double dot IP. Okay, the machine code stores this address, okay, and the corresponding assembly language code. Okay, the physical address then is put on the address bus by the CPU to be decoded by the memory circuitry. Okay, so that is the process on how the instructions is executed. Okay, all right, for example here, so we have, okay, the logical address at this location 1132.0.100. Okay, so we have the machine language of opcode and operand as B057. Okay, B057. So we should do here. All right, so we have, let's see, we want to move, okay, 55, okay, sorry, 57 to AL. Okay, so 57, okay, 57 is moved to the AL. So for the code over here, it still remain as B0, and then operand is the B7. So the opcode is B0, move the AL. Okay, and then the logical address, okay, is at 1132.0.100. Okay, all right. So we also have removed the command of 86 to DH. So we have B6. Okay, we have B6 as the moving command for the DH, and 86 is the value. Right, so you look here. So we have 72 and also 72 back. So over here, DL, so it is mentioned as B2. Okay, it is mentioned as B2. All right, so let's say we have now DX. Okay, so over here we are moving DX into the CX. So we have this code as the machine language. All right, so it will be different. If it is value, then we put the value at the back. Okay. All right. So similarly for the other type of machine language and the assembly language. Okay. So this is what is coded by the programmer. Okay. This is what is read. Okay. This is what is read by the computer. And then this is what is executed. Okay. What is executed at the microprocessor. Okay. Right. So that's the process of fetching and execute in the microprocessor. Okay.
Okay.
Yes.
Is it output is always for AL always B0, and then for DX always D1 for
Okay.
operands?
Actually, there are many types. Okay, because you have moving and addition, right? So the command of moving and addition. So usually, what we have is this. Okay, move. Okay, it can be also in terms of other number. All right. So you can look here that. All right. So for AL, okay, moving AL, so the code is B0. Okay, and moving DH, the code is B6. Okay, and moving CX, the code is B2. But for moving CX, the code is 89, and moving BH, the code is 88. Okay, the code is already the opcode defines what is the what we call the instruction. Okay, what is the instruction given? Okay, what is the instruction given, and then the value after that. So it combines of the opcode and operand. Okay. Okay, I will give more example after this. So let's discuss about that. Okay, let's say here. Okay, we have the instruction of move AL 57. Okay, the similar code. Okay, for the machine code is B057. Okay, and the B0. Okay, of course, the physical address, okay, we look here, the physical address, because it starts from here, so we have 11320 added with 0100. So 1132 added with 0100. So we have 1420. Okay, so this is our physical address. Okay, so physical address is the steps. All right, so it is the steps. Okay, the equivalent of the assembly language is to the machine code. Okay, so first the assembly language, because it is in the sequence, right? So when we instruct the people, okay, when we instruct the machine, we need to give that in sequence. Let's say, okay, now I want to move the value number 1 to the word register. Okay, now I want to add. Okay, now again I want to move. So it is by sequence, one by one. Okay, so the assembly language is first translated into the machine code. So the machine code to move, okay, to move to what register is the opcode, and then the value is the operand. Okay, so usually the opcode is, okay, the opcode is executed first, and then after that the value is executed. All right, for example here, you look. So we have the B0. So this is mentioned at the physical address of that. Okay, and then 57 is the consequence of the next physical address. Okay, and then you do the next command or next instruction, so it will follow. Okay, so this will add up to the physical address. And then for the logical address, you will just see, okay, the increment, okay, starting from the initial number to the maximum number of instructions given. Okay. All right. So the byte address, okay, let's say this first address contains a B0, okay, the opcode for moving a value into register AL. So this is what I mentioned, right? So this specifically move AL or move move AL, move AX, and so on will be different. Okay, it will be different code for the opcode because we can only have what is the maximum, or what is the maximum code that can be coded. It is up to 256 instructions. Okay, as you remember, it's up to 256 instructions because it is a 8-bit, okay, 8-bit number. All right, so this is an 8-bit. So for the 8-bit register, so we can have up to 2 from 0 up to 255, or equivalently is 256 instruction, but usually 0 is not used, so 255 instructions that can be used to store the command of addition and, okay, add or move. All right. Okay.
Okay, Doctor.
Yes, you have any question?
For this one that we learn right now is combined. Like
Which one?
as we saw before is BO B057, right? But for this one is execute one by one.
Yes, it is execute by one. So it is usually the instruction, okay, first it will give you the opcode and then followed by the operand. Okay, opcode and operand. Okay, so that's why you look here. Okay, so at here, after that it jumped to 102 because this is actually the shortcut. All right, this is the shortcut. So B057, so it needs to have 1132.0100 and also 1132.01, okay, 01, okay, 0101 to execute this instruction. That's why you see here the increment, okay, the increment in terms of 2, 2, 2, and 2. Okay. All right. Okay, so this is the real one. Okay, so this is expanded. So this is actually summarized version. So this is summarized version, but this one is the expanded one. Okay, so you have opcode and operand, opcode and operand, opcode and operand. Okay, so assume that we have a program to add 5 bytes of data, okay, such as we want to add 25 page, okay, 12, 15, 1F, and 2B. All right. So one way to add them is like this. So we have, okay, first we initialize our AL. Okay. So AL will be now 0, 0, and then we add 25 to AL. Okay. And then AL becomes 25, and we add 12 to AL. So the AL becomes 37. All right. And now we add more to AL, and we add again and again until to B, and then we get the results of AL. Okay, so in this program, so the data and code are mixed together. All right. If the data changes, okay, the code must be searched for every place it is included and the data retype. Okay. So from this arose the idea of an area of memory strictly for data. Okay. So inside the memory, so either we can just store the data or code. Okay. So because we need to actually, the code is actually the fixed program that we can do. So why not we just fix the location of the code, and then the data, because data can be added and erased at any time, right? So that's why for the certain location of the memory, codes must be stored. For example, you want to have the move AL, so what's the code? Add AL, so what's the code? Add AX, so what's the code? Add BL, what's the code? Okay, so the code is already fixed. Okay. Okay, that's why in the 86 microprocessor, the area of memory set aside for data is called the data segment. And then the data segment uses register DS as an offset value. All right. The debug assumes that all numbers are in hex. Okay. So no H suffix is required. Okay. MASM assumes that they are in decimal. Okay. Okay, so this is actually the difference between two type of what we call assembler, okay, that can be used to program the microprocessor. So in the debug, so we don't need to write H, but in the MASM, H must be included, okay, because the value are assumed in the decimal. Okay. Okay, we look into how data can be stored in data segment. Program rewritten so that it can be used for any set of data. All right, so let's say we have the data segment offset begins at 200, and then the data is placed in memory locations. Okay, we have the DS, so the data segment. All right, we have the data segment 0200, 25, okay, 01, 12, 02, 15, 03, 1F, 04 to B. Okay, so the program can be written as follows. Okay, so AL, so first we initialize the AL, so now AL becomes 0, move AL 0, and we add AL in the bracket, so 0200. So we have the data segment already, so we just call that. So that is 25. So we add 25 to AL, and then we add 0201, and then consequently we add at 0202, 0203, and 0204. Okay, so this is similarly, we can add the value to AL. Okay. All right, so the address is enclosed in brackets. Okay, so which indicates the operand represents the address of the data and not the data itself. So this is the operand for the data, actually. Okay, meaning that we stored the data inside this operand. Okay, so whatever it is we stored here will be called again over here. So we just add the value. Okay, but if the bracket not included, okay, then we add the value of 0200. It's not the value here, 25. So that's the difference. Okay, so the program will run with any set of data. Changing the data has no effect on the code. So if the data had to be stored at a different offset address, the program would have to be written. Okay. A way to solve this problem is to use register to hold the offset address and before each add, increment the register to access the next byte. Okay, so this is the problem when we had to store the data at different offset address. Okay, so we have to re-return that. So without having want to re-return the data, because we still want to use that, so we can use register to hold that offset address. Okay. Okay, so ADC allows only the use of registers BX, SI, and DI as offset register for the data segment. Alright, so the term pointer is often used for a register holding an offset address. Okay. Alright, I think I will stop here for today. Alright. So we will do a little bit revision on this on Thursday. Okay, so later we will finish this data segment. Okay. Any questions so far?
No, doctor.
Alright. So let's turn on the camera so we can take picture together for your attendance. Okay. All right. I will give you some assignment later within this week. Okay. So wait for the instruction in the WhatsApp group. So I will share that. Okay. So you will have a little bit exercise to test the understanding of you on the topic that I have teach so far. All right. Okay. Let's take the picture. All right. 10, 9, 8, 7, 5. Sorry, 7, 6, 5, 4, 3, 2, 1. So smile, everyone. Okay. One more shot, please. Okay, and one more. Last one. Okay, thank you everyone. So I see you again on Thursday. All right. Okay, so any question you can ask me on the WhatsApp or by email. All right, so that's it for today. Bye-bye. Okay, Assalamualaikum.
Thank you, doctor.
Waalaikumsalam.
Thank you. Bye bye, doctor.
Thank you, doctor. Thank you, doctor.